Many substances expand on heating and contract on cooling. An increase in the dimensions of a body due to an increase in its temperature is called thermal expansion. For example, the volume of the mercury in a mercury thermometer changes with a change in its temperature. Let's look at some examples of thermal expansion of substances that we come across in daily life. Rails are produced in fixed lengths, and fish plates are used to join them. The gaps provided between rails allow them to expand during summer. Expansion joints are provided while constructing bridges. When the temperature of any metallic body is increased, its length, surface area, and volume may increase. Expansion along length is defined as linear expansion. Expansion of the surface area of a solid is called areal expansion, and expansion of its volume is called volume expansion or cubical expansion. Let us consider a thin metal rod of length L at a temperature T. It is experimentally observed that the change in the length of the rod, delta L, is directly proportional to the change in its temperature, delta T, and also directly proportional to the initial length of the rod. Thus, we get equations 1 and 2. Combining equations 1 and 2, we get the expression delta L equal to the product of alpha L, L delta T, where alpha L is the proportionality constant called coefficient of linear expansion and is characteristic of the material of the rod. The fractional change in length delta L by L is equal to alpha L into delta T. Similarly, the fractional change in the area is experimentally found to be directly proportional to the change in the temperature. That is, delta A by A is equal to alpha A into delta T. That is, the fractional change in the area, delta A by A, is equal to alpha A into delta T, where alpha A is the coefficient of areal expansion. If the volume of a solid body is V and delta V is the change in volume for a change of temperature delta T, then delta V is equal to alpha V into delta T, where alpha V is called the coefficient of volume expansion. Though the coefficient of expansion is a characteristic of the substance, its value depends on its temperature. For many solids, expansion is analogous to photographic enlargement. For example, if a metallic sheet with identical holes, as shown, is heated, then the expansion is proportionate in all directions. The length and breadth of the sheet, radii of all the holes, and the distance between two holes all increase proportionately. Substances that expand at the same rate in all directions are called isotropic substances. For a perfect isotropic material, the coefficients of thermal expansion are related as alpha V equals to 3 alpha L and alpha A equals to 2 alpha L. Let's prove the identity by considering a cube of length L naught. Its total surface area A naught equal to 6 L naught square and its volume V naught equal to L naught cube. when the temperature of the cube is increased by delta T, let the length of each side be increased by delta L. Therefore, the length of the side after expansion L equals to L naught plus delta L. Change in area delta A equals to 6 into L naught plus delta L whole square minus 6L naught square. This is equal to 6 into delta L square plus 2L naught delta L. The term delta L square can be ignored as the value is negligible. Then we get delta A is equal to 6 into 2L naught delta L. Now, by dividing delta A by A naught, we get 6 into 2L naught delta L by 6L naught square. On further simplification, we get alpha A equals to 2 alpha L. Let this be equation 1. Change in volume delta V equals to L naught plus delta L whole cube minus L naught cube. This is equal to L naught cube plus 3L naught square delta L plus 3L naught delta L square plus delta L cube minus L naught cube. The terms delta L square and delta L cube can be ignored as their values are negligible. Then we get delta V is equal to 3 into L naught square into delta L. Now by dividing delta V by V naught, we get 3 into L naught square delta L by L naught cube. On further simplifying, we get alpha V equals to 3 alpha L. Let this be equation 2. Let us now look at the expansion of solids at an atomic level. In a solid, the atoms are arranged in fixed positions. Expansion of a solid indicates that the average separation between the atoms is increased. As the temperature increases, the atoms vibrate with more vibrational energy, and the amplitude of vibrations also increase. The graph shown is the potential energy curve for two adjacent atoms in a solid as a function of their internuclear separation. Since the potential energy curve is an asymmetric curve, the average separation between atoms increases as temperature increases. As liquids do not have a specific shape, they do not have linear and aerial expansion as solids do. They have expansion in volume only. When a liquid in a container is heated, both the liquid and the container expand. Hence, for liquids, we have two categories of expansions, namely real and apparent. The apparent expansion of a liquid is the expansion that appears. The apparent expansion of the liquid is equal to the real expansion of the liquid minus expansion of the container. Unlike other liquids, water exhibits irregular expansion between 0 degrees centigrade and 4 degrees centigrade. If the temperature of water is raised from 0 degrees centigrade to 4 degrees centigrade, instead of expanding, it actually contracts. This means a given mass of water occupies least volume and, as a consequence, will have maximum density at 4 degrees centigrade. This anomalous expansion of water enables aquatic animals and plants to survive in water. Lakes and ponds freeze first on the upper surface of water. The frozen water body, which is the ice, floats on the denser water. When a solid, liquid and a gas are heated, the gas expands more than the solid and the liquid. For ideal gas, PV is equal to mu RT. Let this be equation 1. If the pressure of the gas is constant, on differentiating equation 1, we get P delta V equals to mu R delta T. Let this be equation 2. On dividing equation 2 by equation 1, we get delta V by V is equal to delta T by T. But delta V by V is equal to alpha V into delta T. Hence, for an ideal gas, alpha V is equal to 1 by T. For gases, the coefficient of volume expansion is inversely proportional to the absolute temperature of the gas. Let us now discuss thermal stress. Consider a rod rigidly fixed at both ends to prevent expansion. If the temperature of the rod is changed, then the stress that develops in the rod is called thermal stress. The stress developed in a body when not allowing it to expand while heating is called thermal stress. If the length of the rod is L and delta L is the change in its length for a temperature change of delta T, then delta L by L is equal to alpha L into delta T. Let this be equation 3. If the rod is rigidly fixed, then thermal stress is expressed as F by A, which is equal to Y into delta L by L, where Y is Young's modulus of the material. Let this be equation 4. From equations 3 and 4, thermal stress is expressed as Y into alpha L into delta T. The force F acting on the rod must be equal to the product of Y, A, alpha L and delta T.